Hello viewers, welcome to our channel. In this demonstration, we would analyze the radial inflow in a perforated pipe. It's placed inside a pipe. Water is entering from the outer pipe and then flowing through these perforations towards the outlet in the inner pipe. From this tutorial, you would be able to learn how to create a perforated pipe geometry in ANSYS. Application of pattern and rotate tool in geometry creation. How to create an axisymmetric model from the full geometry. Meshing of the geometry using default element sizes. Adaptive sizing in ANSYS Meshing. Solver setup in ANSYS Fluent. Results post-processing in CFD Post processing. Open the ANSYS Workbench, double-click on ANSYS Fluent or drag it to the project schematic window. Right-click on Geometry and select New Design Modeler Geometry. Keep the default unit as millimeter. Select the XY plane to create the sketch. Click on Z-axis to make the sketch plane normal to the screen. Go to Sketching Toolboxes. Select the Circle tool and draw two circles for the inner pipe sketch. Put the dimensions. Click on Generate. Select the sketch and click on Extrude. In the geometry box, click on Apply. This means the sketch is to be extruded. Select the operation as Add Frozen. This option will keep the body as a separate entity than the other parts, which is to be created further. Enter the depth of extrusion as 500 mm. And select the direction as both symmetric. This would extrude the sketch 500 mm each in both directions of the sketch plane. Then click on Generate to create the geometry. Select the ZX plane to create another sketch. Draw a circle at the origin. Put the dimension to it. Extrude this circle 100 mm in both the directions. Click on Generate. Now pattern this body along positive Z direction. Select the body, click on Apply. Select the direction by selecting the Z-axis. Put the offset distance and number of copies. Then click on Generate. Again, do the similar pattern for negative Z direction. Click on arrow to switch between directions. Go to Create menu, then select Body Transformation, then Rotate. Select all the 5-cylinder and click on Apply in the box. Then choose the axis as the Z-axis. Enter the angle of rotation as 90 degrees. Preserve the parent bodies by selecting the Preserve Body option. Click on Generate to create the copies. Now we need to subtract these bodies from the cylinder to create the perforations on this. Go to Create menu and select Boolean. In the operation, select Subtract. Select the hollow long cylinder as the target body and the smaller cylinders as the tool bodies. In the Preserve Tool Bodies option, select No, as we would need the perforations only. Now, insert a new sketch on the XY plane and draw a circle with center at the origin. Put the dimension. Select the Extrude option to extrude the circle. Select the sketch and click on Apply. Enter the operation as Add Frozen. Put the depth of extrusion as 500 mm along both the direction in equal length. Click on Generate. Now we need to separate the inner geometry from the outer one. Go to Create menu and select the Boolean operation. Select the outer domain as target body and the inner perforated cylinder as the tool body. In this case, keep the Preserve Tool Body option on as we need to have the inner pipe geometry. In the current problem, you can delete the inner pipe geometry as there is only fluid flow through this, so only the fluid domain is sufficient to obtain the result. If there is any heat generation or any other analysis, we need to keep the inner perforated pipe geometry. Select the two bodies and make it one part. Select the XY plane, insert another sketch to cut the quarter of the geometry. Take the polyline tool, draw the geometry. Right-click and select the close end. Extrude the sketch 500 mm in both directions. Select both symmetric options to extrude in both directions. Use Boolean tool to subtract the bodies to keep the quarter part and subtract the rest part. Use the Control key and select both the cylinder geometry. Select these as the target body and the outer part as the tool body. Choose the Preserve Tool option as No, so the outer part will be deleted along with the cylinder parts. Geometry is now complete. Close the window and proceed for meshing. Open the Meshing workbench. Click on Mesh, go to Details of Mesh. Change the default mesh size to 0.003. Open the sizing option and enable the adaptive sizing option for a better mesh. Enter the optimum resolution of 7. Right-click on Mesh and select Generate Mesh. All tetrahedral cells are generated. Check the mesh statistics. As the number of elements exceeds the permissible size for the academic version, we need to decrease the number of meshed elements. Right-click on the mesh. Select Insert then Method. Now select all the geometry. Click on Apply. Select the method as hex dominant. Again right-click on the mesh. Insert Sizing. Select the Edge Selection tool and select the edges of the inner perforated cylinder. Hold the Control key and select 4 edges of the cylinder. In the type select Number of divisions. Enter the number of divisions. Select the behavior as hard, this would suppress the default mesh setting. Disable the Show Mesh option to see the geometry properly. Select the edges and insert sizing. Enter the number of divisions and mesh behavior setting. Again insert sizing to provide edge sizing to the inner edges of the domain. Right-click on Mesh and select Generate Mesh. Mesh generation is completed. Mostly hexahedral cells are generated. We need to further decrease the number of elements to match the academic version mesh limit. Let's increase the default element size to 0.005. Now it's within the limit. We can now proceed for the named selection of boundary surfaces. Use the Face Selection tool, select a face, and name it as the inlet. Select the end face of the perforated pipe and name it as Pipe Wall 1. Select the inner face and name it as the wall. On the other side, select the inner face and name it as an outlet. Select the outer face and name it as Wall 2. Name the end face as Pipe Wall 2. Select all the profile of the flat side and name it as Symmetry 1. Similarly, select all the faces of the other side and name it as Symmetry 2. Select the Body Selection tool. Select the outer domain and name it as the Fluid domain. Select the inner perforated pipe geometry and name it as the Solid domain. Cross-check all the named selections and make sure that one face should not be named twice. Right-click on Mesh and select Update. The mesh would be linked with the solver. Now close the meshing and open the Fluent Solver setup window. Right-click on Setup and select Edit. Enable the double precision option and click on Start. This is the Fluent Solver setup window. At first, check the loaded mesh. Check and make sure that the minimum volume should not be negative. Check the quality of the mesh. Go to Models, select the Viscous model. Select the Laminar Viscous model and click on OK. Click on Materials and open the Fluent Material database. Select the default properties for water. Click on Copy. Click on Change or Create, then close it. Now go to the cell zone conditions and select the fluid domain. Click on Edit, then assign the water liquid as the material in this fluid domain. Keep the default aluminum as the solid zone material. Now we would assign the boundary conditions in this problem setup. At first, arrange the boundary surfaces as per their types. Select the inlet boundary and click on Edit. By default, velocity inlet boundary condition has been assigned to it. Keep the default pressure outlet boundary conditions at the outlet. All the symmetry boundaries have been assigned by the solver by the boundary name. Also, all wall boundaries have been assigned properly, no need to again reassign those. Select a pressure velocity coupling scheme as Simplec. Select green Gauss cell-based spatial discretization scheme for gradient. Keep the pressure as second order and momentum as second order upwind. Click on Monitor and select the residual option. Enter the required residuals as 10 to the power minus 6. The lesser be the residuals, the more accurate be the results. Click on Initialization, select the standard initialization. Select Compute from Inlet and click on Initialize. Click on Run Calculation. Enter the number of iterations as 500, as we don't know how many iterations it will require for the solution to be converged. Then click on Calculate. Calculation got completed. There is no convergence of the current solution. As there are not much variations in the graph, we can stop here and proceed for results. Save the solver and close the Fluent. Now open the CFD Post processing results. Let's first observe the streamlines. Insert the streamlines and select Start from Inlet. Click on Apply. As this is a quarter part of the full model, so to get the streamlines for the full model, we need to replicate the streamlines along various sections. For this we need to take the help of Reflection or Mirroring Render tool. Tick out the Apply Reflection Mirroring option. Select the plane about which you want the reflection. Then click on Apply. To create further copies, right-click on Streamline 1, then select Duplicate. To create the final copy, we need to take the help of the Rotation tool. Tick the Rotation option. Enter the angle of rotation. Then click on Apply. Hide the geometry wireframe to observe the full streamline properly. Now let's observe the flow animation using the Solution Animation option. Select the Quick Animation option. Select all the streamlines, then select the animation speed and click the play. Close the animation. Let's see the velocity contour. Go to Insert bar and select Insert Contour. Select the variable as the velocity. For the location, click on the dots near the location drop-down menu, select the symmetry faces of both the domain. Click on OK. Increase the contour bands to observe the contour variations properly. Click on Apply. Hold the Control key and mouse scroll to rotate the contour image. Modify the contour legend view to a general fixed precision value. You can also get contours of the full domain using the reflection mirroring option as done in case of streamlines. Click on the camera icon to save the contour image file. Enter the image size and the folder location. Click on Save. Now we would observe the velocity vector in this simulation. Select the Symmetry wall location and click on Apply. You can also modify the arrowhead type and symbols. Save the contour image for further use. With this, let's conclude this demonstration. Please comment below for any suggestion or query. Hit the like button if you find this video helpful. If you are new to our channel, then please subscribe. Thank you. Stay safe.